Let's start our class from where we stopped last time. So today we are going to look at output machine. So here is a typical diagram of an output machine. So in solving problems related to output machine, we are going to apply Newton's second law. Newton's second law. So here, looking at this diagram, to resolve or solve problems related to this, the first thing to do is to detach the two masses hanging on the pulley. We have mass 1 on the left, mass 2 on the right. And just looking at the diagram, we can see that mass 1 is less than mass 2. And that shows why mass 2 is moving downward and mass 1 is moving upward. So if we are to apply Newton's second law, which is F net is equal to MA. F net is equal to MA. So we are going to consider them separately. We'll consider this separately and consider this. So let's take the first one. This is 1 and this is 2. So for 1, since the mass is going up, it means that the tension force, this tension force is greater than the weight force. Now, these are the two forces acting on this mass. So, like I told you before, that when two vectors are moving in opposite direction, you add. Force is a vector quantity. So we have two forces here, the tension force pointing upward and the weight force pointing downward. So the two forces are in opposite direction. You subtract the smaller force from the greater force. And how do we know the smaller force? The smaller force always move in the direction of the greater force. Or the greater force pulls the smaller force to itself. Where the direction of the object is, that is the direction of the greater force. So since the object is moving upward, the direction of the greater force is upward, which is the tension. So our F net will be T minus M1G. T minus M1G is equal to M1A. I said we are considering the first mass in isolation. So now we can find T by moving M1G across the quality sign. So T becomes M1A plus M1G. So that is our T. We can say this is equation 1. Now, coming to the second part. Here we have the mass 2. The mass 2 is pointing down, which implies that it has a greater M2G is of a greater force than the tension. The same thing applies here. We have tension, that is the force on the rope, and we have the weight force. Two forces. The tension is pointing upward, the weight force is pointing downward. That is here. The tension is pointing upward, the weight force is pointing downward. And since the object, the mass is moving downward, it means that this force is greater than the tension force. So we can apply Newton's second law to this scenario by writing that m2g minus t is equal to m2a. So that is equation 2. Now, if we combine equation 1 and equation 2, in equation 1 we have, in equation 1 here, we have T is equal to M1A plus M1G, while in equation 2 here we have M2G minus T is equal to M2A. So we can substitute equation 1 into equation 2 to replace T. So when we do that, our expression will be M2G minus, in bracket, M1A plus M1G, in bracket, is equal to M2A. So now we can solve for acceleration. To solve for acceleration, we open the bracket and move the acceleration term across the equality sign. So that will give us M2G minus M1G is equal to M2A plus M1A. So here we have G common, so we can write G into M2 minus M1 is equal to A is common here, A into M2 plus M1. M1. So we make A the subject of the formula, and that will give, that is by dividing through by this, by M1, M2 plus M1. So that will finally give us A becomes G into M2 minus M1 all over M2 plus M1. So that is our A. So now, what if mass 1 is greater than mass 2? That is, this mass is greater than this mass, such that this is coming down and this is going up. We can still apply the same formula to find the acceleration. However, in this case, since mass 1 is greater than mass 2, we will alter the arrangement in the numerator here. So this time we now have M1 minus M2. Every other thing remains the way it is. Only the up that will change from M2 minus M1 to M1 minus M2. So you subtract the smaller mass from the greater mass. Subtract the smaller mass from the greater mass. So the first case where M2 is greater than M1, we subtract M1 from M2. Now the second case that I just explained, where M1 is greater than M2, you subtract M2 from M1. So that is how to solve problems related to attitude machine. So remember that you may be given acceleration and other quantities and asked to find tension. In this equation, we have tension, we have mass 1, we have mass 2, we have acceleration, and then we have G. G is a constant. But these four quantities, M1, M2, tension, and acceleration, you could be asked to find any one of them. You could be asked to find any one of them. So prepare your mind for that. Don't think that you'll be asked to find only acceleration. So let's move on to an example here. So here we have an example. In the attitude machine shown in the diagram, if M1 is 0.4, if M1 is 0.4, this is M1 is 0.40 kg, and M2 is 0.60 kg. What is the magnitude of the acceleration of the system? So the magnitude A will be equal to G. Since M2 is greater than M1, it means that we are going to subtract M1 from M2. But at the denominator, we add them. At the numerator, we subtract. At the denominator, we add them. So this is how the equation will look like. So we substitute. Let's take acceleration due to gravity as 10. So that will be 10 into mass 1 is, okay, mass 2 is 0.6. 0.6. Mass 1 is 0.4. Then we add 0.6 plus 0.4. So this will give us, at the numerator, 0.6 minus 0.4 is 0.2. So 10 times 0.2 will give us what? 2. Then at the denominator, we have 0.6 plus 0.4 is 1. So our answer will be 2 meters per second square. A is equal to 2 meters per second square. Now, quickly, How many of you are there?
We are here, sir.
So
Okay. So I want to give you something to solve now, and tell me the answer. Now, with what we have here, if this is M1, and then this is M2, and then M1 is 10 kg, while M2 is 5 kg. Find one, A, acceleration, and 2, tension. So solve that quick. I give you 5 minutes to solve it, and let me have the answer. Damn This, this is 5, and this is 6. Our mark question 3, and question 1 and 2. Our mark question 1 and 2, just 5 and 6. You want to start marking? Okay, well, let me quickly show this. Any answer?
the acceleration is 3.3
Okay,
meters
and
squared.
tension. What's tension?
So the tension should be around 66.4.
Good, 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 good. So I'm impressed with that. So we can move on. So let's look at linear momentum and its conservation laws. Now, momentum is defined as a product of the mass and velocity. So according to the law of conservation, the sum of linear momentum before collision is equal to the sum of linear momentum after collision. Now, you have to understand that when we talk of collision, it implies that two or more bodies will come together. So here we consider two bodies colliding, coming together to have impact on one another. So if we have body A and body B moving in opposite direction, since they are in motion, body A will have its own momentum, which is the mass and the velocity of body A. Then body B will also have its own momentum, that is the product of the mass and velocity of body B. Both of them are moving at different speeds, and then they collide in opposite direction, collide with one another. Now, after the collision, it is possible that the two objects will move in different directions. So, according to the law, the momentum before collision is equal to momentum after collision. So we can write an expression as P. P is for momentum. So we can say P1 or PI, which is initial, is equal to PF, which is final. So now that we have two objects with mass moving at a given velocity, their velocity before collision is initial velocity. And velocity after collision, which is the final velocity attained, is final velocity. So we have M1, U1 for the first body, and then M2, U2 for the second body. That is before collision. And then after collision, the first body will have M1, V1, while the second body will have M2, V2. So that is the law of conservation of linear momentum. Now, that is not all about momentum or linear momentum. The collision changes the velocity of the objects involved. Now, the final velocity is different from the initial velocity. And since kinetic energy of the object depends on velocity, the kinetic energy also changes. Remember that kinetic energy is the energy a body acquires by virtue of its motion. Whenever an object is moving, it will acquire kinetic energy because it's moving with a speed. And we know that kinetic energy is half mv squared. So speed is there, mv squared. As the speed changes, the kinetic energy also changes. So collision could be elastic or inelastic depending on what happens to the total kinetic energy of the entire system. Like we said before, the momentum before is equal to momentum after. So we have kinetic energy before and kinetic energy after. So the total kinetic energy of the system, if it is conserved, then that is elastic collision. If the total kinetic energy is not conserved, by conserved, I mean if it is not the same, then that will be inelastic collision. So when the total energy is the same, just as the total momentum before and momentum after is the same, then we have elastic collision. But if the kinetic energy is not the same, then we have an inelastic collision. Then another thing we should also know is in an inelastic collision, since the kinetic energy is not conserved, it means that there will be a loss of energy. And from conservation of energy, we know the energy cannot be destroyed nor created. So the loss of energy may not actually be just lost in any way, it will be transformed to another form of energy. So that transformation could come in the form of thermal or in the form of a sound energy. So in inelastic collision, total kinetic energy is not conserved, but transformed to sound or thermal energy. Another aspect of this subtopic is elastic collision could be perfect or not perfect. However, when we say perfectly elastic collision, it is an idealized situation where we consider external forces and friction to be completely negligible. That is why we say idealized, because ordinarily, when object is in motion and is colliding with another object, there is no way you can rule out friction. There is no way you can rule out air resistance. But we assume that all these conditions are in a perfect state. So that is talking about perfectly elastic collision. All external forces and frictions are negligible. In this kind of collision, the colliding particles do not disintegrate or join to themselves. And therefore, the momentum and kinetic energy are perfectly conserved. They are perfectly conserved. But in a perfectly inelastic collision, where the two objects sticks together after collision so that the object have the same final velocity. So in a perfectly inelastic collision, when they collide, they bounce off, move their separate direction. But perfectly elastic collision, they collide and then the both colliding object moves in the same direction. Let me give an example of a trailer and a small sports car colliding headlong. So when that happens, of course, we know that the trailer will move the small sport car in its direction. Because of the power of the trailer, it will move the smaller car in its own direction. So both the smaller car and the trailer will assume the same velocity after collision. So that alters the former equation we have where the two objects, after colliding, move in separate paths and attain different velocities. But this time they are going to have the same, a common velocity. So we have M1, U1 for the first object, M1, M2, U2 for the second object. And then after collision, we have a common velocity, just one V. There is no V1, there's no V2. So we have M1 plus M2 all in bracket times V. So that is the equation for calculating perfectly inelastic collision. Now, the extent to which the collision is elastic or inelastic is described by what we call coefficient of restitution. So coefficient of restitution is the ratio of the relative speed after collision to the relative speed before collision. Remember, we have speed 1 and 2, initial, speed 1 and 2, final. So the difference between the speed, the final speed, over the difference between the initial speed is what our coefficient of restitution represents. And if the coefficient of restitution is equal to 1, it implies a perfectly elastic collision. And if it is 0, it is a perfectly inelastic collision. So now, if it is between 1 and 0, of course, between 1 and 0, we have half mark, which is 0.5. So anything greater than 0, from 0.5 above towards 1, we have elastic collision until when it gets to 1, that is when it is perfectly elastic collision. And then from 0.5 going down to 0, we have inelastic collision. And when it gets to 0 proper, then it is perfectly inelastic collision. So here we have a little example to play with. Two cars, masses 2,500 kilogram and 1,200 kilogram, have an initial velocity 40 meters per second and 10 meters per second, respectively. After collision, the cars locked bumpers and travel along X direction. If the total momentum is conserved, determine the velocity of the cars just after collision. Now, one important aspect of this question is after collision, the two cars lock bumpers and travel along x-axis, meaning they assume the same velocity, they move in the same direction. So in that case, we are going to apply perfectly inelastic collision method to solve it. And that will be, okay, let me use my marker here. So we are going to use M1, U1 plus M2, U2 is equal to V M1 plus M2. So M1 is 2,400 times 40. 2,500 times 40 plus 1,200 times 10 is equal to V 2,500 plus 1,200. So this will give us 3,700. 3,700, while this will give us 100,000 plus 12,000. That is 112,000. 112,000 divided by 37,000. That will give us our V. So that is that gives us 30 meters per second. 30 meters per second. That is the speed at which both of them move together. Right. So let's make progress. So let's look at center of mass and center of gravity. The term center of mass and center of gravity are used synonymously in a uniform gravity field to represent the unique point in an object or system which can be used to describe the system response to external forces and torque. Now, when you hear the word center of mass, what will come to your mind is the center or the balance point of the object, a point where the object can be kept in a balance, in an equilibrium state. So that is center of mass. So center of mass can be considered as the point where the entire mass of the body is supposed to be concentrated. So it has a general formula, especially now. We have, for instance, we have here two masses. If we have two masses, the formula here for the center of mass is the mass of the first object and multiplied by the distance from the object to the distance of the object from the origin plus the mass of the second object times the distance of the second object from the origin. So we have here mass 1 and mass 2. Mass 1 is x1 from the origin. From here to, this is the origin, the starting point. So from here to here is x1. Then mass 2, from where it is to this is x2. So our center of mass is given as this: m1 x1 plus m2 x2 over m1 plus m2. Now, if we have three masses, it will be plus m3 x3 over plus m3. If we have four masses, the same way, we keep going. The number of masses, if we have 10 masses, like that, you keep adding them.
Sir,
Yes.
sir, I don't understand that diagram.
You don't understand this diagram?
Yes, like what exactly is it supposed to be, like a balance or?
Yeah. Now, look at, let me give you this. Do you understand this diagram?
Yes.
Understand this diagram?
What do you mean?
What I just drew, do you understand the diagram?
It's supposed to be a graph.
You have not seen this kind of diagram before?
No.
You have not seen it before. How did you pass your WAEC? You have not seen this kind of diagram before?
Maybe
This is Y positive, Y negative, plus
yes.
X
Yes,
and minus X.
yes,
You have not seen this diagram before.
I have.
So it's the same now. So if I have this kind of diagram and I have an object here going this way, so this is the diagram. This is X. This is negative X. This is positive Y. This is negative Y. So this point is called what?
0.
That is origin, isn't it?
Origin, yeah, origin.
Yes, so that is the reference point. Anywhere I am standing will be made reference to this point, isn't it?
Yes, sir.
Okay, so see that picture, have that at the back of your mind when you are looking at this. So here I have a mass. Here, this is the origin. Then this is another mass. Though these two masses, let's say this is a beam, like a ruler, then here is the balance point. But the balance point, which is the center of gravity, does not really matter now. So from this point to this, and this point to this, that is what we are looking at. Did you
Okay.
get?
Yes, yes.
Okay, where the object is from the origin, where the two object is from the origin. So now, if you understand that, object 1 is x1 from the origin. Object 2 is x2 from the origin. So now, where will the center be? If I want to find the center to balance these two objects, that is why you have PHY-CM. That is this center. This center. You know, if you have, let's say you have a book in your hand and you want to balance it using your one finger, you will be trying to put the finger one side, the book falls, you try to move it to another side, you try to move it to another side until you get a point where the book can stand on your finger, isn't it?
Yes.
So what you are doing is like you are just trying to speculate, trying to do trial and error by moving the finger, adjusting the finger until it gets to a balance point. But by this formula, if you apply this formula, you will know exactly where to put the balance point. So that is what this center of gravity is teaching us. So you don't need to do trial and error. You just do your calculation and then you go straight to that point and put your pivot there and the object will balance.
Okay, sir.
Okay.
But in like real life, where would the origin be? Like, what would we see the origin as?
The origin will be anywhere you choose.
Okay.
Yes. It could be, if the origin is here, if you put the origin here, it means that this mass will have no x.
Okay.
It means that this is 0. So you are going to have only that equation, m2 x2 over m1 plus m2. That is what you are going to have.
Okay.
Yeah. So here, like I explained before, we have multiple masses aligned. So the formula remains the same. You add, you multiply the, find the product, that is the mass and the distance from the reference point, all of them, each of them, and add them together, and then add their common masses. So when you divide, you get your center of gravity. We can apply it to two-dimensional situation and three-dimensional situation. By two-dimensional situation, I mean we apply it to x and then to y. For three dimension, we have x, y, and z. Now you do this separately. You don't combine them. That is why you see the formulas. They are the same method, the same technique, but they are separate. They are separate. This is for x, this is for y, and that is for z. So let's look at this example. 2-point masses, 3 kg and 5 kg, are at 4 meters and 8 meters from the origin on x-axis. You are playing games this morning. 2-point masses, 3 kg and 5 kg at 4 meters and 8 meters from the origin on x-axis. Locate the position of center of mass of the 2-point masses. 1, from the origin, and 2, from 3 kg. So now, here we have just 2 masses. We have 2 masses, and we are asked to find the center of origin, center of mass, when the object from the origin, and then when the origin is moved to 3 kg. So our formula remains the same. PHY-CM will be M1 is 3 times, this is M1, this is M2, this is X1, this is X2. So M1 times X1, that is 4, plus M2, which is 5, times X2, which is 8, all over M1, which is 3, plus M2, which is 8. So that gives us 12 plus 40 is 52 over 11. That is 4 point something.
Sir,
Yes.
isn't M25?
5 is M2 now.
You put 8.
I put what, 8? Or you have forgotten the formula?
Yeah,
No.
no, I remember the formula. You put 3 plus 8.
3 plus 5, sir. Below.
Okay. That is 8. Sorry, thank you.
The answer is 6.5.
6.5, bro.
So that is 6.5 meters. So now that is 1. The second one says from 3 kg. So let's assume that here is our origin, and the first mass is here, the second mass is here on a straight line. So here is X1, then here is X2. That is the first case. Now, that this is the origin. From the first mass to the origin is 4 meters. Now, we are asked to find or move the origin to 3. So if we move the origin to this point, it means that we have cut off 4 meters. So the first mass is at the origin, which means the first mass will not have distance. So the first mass is at 0.0. So the mass times 0 will be 0. Then the second mass from where it is to the first mass is 4, because we have cut off 4. So this time we are going to have 20 over 8. So that would be 2.5 meters.
Sir, I don't understand though.
You don't
Please come again.
understand?
Yes, sir.
Yes.
The first one say from the origin, isn't it?
Mm-hmm.
The second one say from 3 kg. So 3
Yes, sir.
kg means that 3 becomes where the 3 kg mass is. That is your origin. You remember someone asked me a question, and I use this to illustrate.
Yes, sir.
sir.
So if this is the origin and the mass is here, and then we are told to move this origin to this point, it means that this mass will not have any distance again, isn't it?
Yes, sir.
Yes.
So if I multiply that mass times 0, it becomes what?
0.
Because the mass is at 0 point. So the distance of that mass is 0.
Zero.
You can't hear you, sir.
Yes. And now, this second mass from the initial question, the second mass to this origin is 8. The first mass to this origin is 4, which means that the two masses, the difference between the two masses is 4 meters. So if I now move the origin to this point, it means that the second mass will have 4 meters away from the origin. So that is why we have 0 plus 5 times 4, 20 over 3
8.
5, which is 20 over 8, 2.5 meters. Is that clear now?
Yes, sir.
Yes, sir.
Okay. Now, center of gravity. Center of gravity of a body is that point where the total gravitational torque on the body is 0. So now if you look at this formula and the center of mass formula, the only difference is addition of G, isn't it?
Yes, sir.
So now, what if the G up and the G down are the same? It means that the G will cancel. That is, this becomes this will become G outside M1 X1 plus M2 X2 and so on, all over down at the denominator. We are going to have G, which is common outside again, M1 plus M2 plus dash dash and so on. So these two G's, since they are the same, they will cancel out, isn't it?
Yes, sir.
So if they cancel out, our equation returns back to center
Normal.
of mass. So center of mass and center of gravity coincides when the field is uniform. That is when we have a uniform gravitational field, the center of gravity is equal to the center of mass. For instance, look at this question. The question says a uniform beam. So that term, uniform beam, as now a uniform beam of 5.0 kg holds up the two masses as shown. Find the center of gravity of the system of objects from the left edge of the board. So we are asked to find center of gravity. However, to solve this problem, since we are told that the beam is uniform, it means that G is the same, both up and down. We have a common G. So the common G will cancel out. Our equation would now be like center of mass. So here, our center of gravity is equal to center of mass. So we are going to use center of mass formula to solve it. So here we go. So we have three objects given to us. So we write out M1G1X1 plus M2G2X2, M3G X3 over M1G plus M2G plus M3G. Because we are given three objects. This is number one. This is number one. The beam itself has a mass. This is number two. And then this is number three. So we are going to have three variables in the equation, which is M1X1 plus M2X2 plus M3X3 all over M1 plus M2 plus M3. X1 is 1, X2 is 3, and X4 is, X1 is 1, X2 is 3, and X3 is 4. Because this 5, the entire length of the beam is 6. This 5 gram is located at the center of the beam. So from the center of the beam down to that point is 3.
So I said that the X2 is 3, right?
Yes, because the 5 kg is at the center of the beam. Look at it. If you look at it, you will see that the 15 kg is at 4 cm from the origin, isn't it?
Yes, sir.
Then the 5 kg is at the center because they said a uniform beam of 5 kg, the beam weighs 5 kg itself. So, and that
Yes.
is at the center of, remember center of mass, the center where the mass of the object concentrates. That is center of mass. So the beam is 5. So it's at the center where the weight of that beam is concentrated. So it's at 3. If you look at where it is, it's a bit away from the 15 kg. And the 15 kg is at 4 cm, 4 meters. So the 5 kg will be at 3 meters.
Yes, sir.
So if you substitute all the values there, we have 2.3 meters. So the center of gravity is at 2.3 meters from the left edge. So here we have another example. The second one precisely, this one, is about 2 dimensions. So we use this for 1. We have how many masses? 1, 2, 3, 4 masses. And we have 4 distances. 1, 2, 3, 4 distances. So when you see distances represented in this form, it means the first one is X, the second one is Y. So if I want to find the center of mass for X, I will use 4 kg, which is M1, and the first 0, 6 kg, which is M2, and 4 for the X2, then 7 kg for X3, then 10 kg for X4. Then when I want to solve for PHY-CM, 4 kg for D0, 6 kg for D0, 7 kg for 5, and then 10 kg for 6. So that is how to solve this kind of problem. It's a 2-dimensional problem. So I expect you to practice it, to solve it. If you solve and you have challenges, you let me know. But I've already sent the materials to you, and the solution is already in the material. So let's look at moment of a force. The tendency of a force to cause an object to rotate about an axis is known as the moment of the force about the axis. It is also known as torque, which is the cross product of the length of the object and the applied force. So look at that spanner. If I want to lose that knot, if I want to lose it, I will raise it up. If I want to tighten it, I will push it down. So the knot is the pivot, while F is the fulcrum, which is the force applied. So the distance from the knot to where the force is applied is noted. So the moment of the force about this system is the force times the distance, force times perpendicular distance. And because it is a cross product, the angle between them is perpendicular, 90 degrees. Sine 90 degrees is equal to 1. Sine 90 degrees is equal to 1, which means that the torque eventually becomes FR, because this is equal to 1. Principle of moment, we have when an object is balanced or in equilibrium, the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. The moment is force times distance, which is also torque. So torque 1 is equal to torque 2. Torque 1 is clockwise moment, while torque 2 is anti-clockwise moment. So here is another diagram to illustrate. If you look at this diagram, we have 4 masses hanging on a beam. So 2 of the masses, M1 and F1 and F2, will be pulling the object down towards the left side, while F3 and F4 will be pulling the object down towards the right side. So F1 and F2 are going anti-clockwise, while F3 and F4 are going clockwise. So the sum of the clockwise moment is equal to the sum of the anti-clockwise moment. So here is an example. If the force applied is perpendicular to the handle of the spanner as shown in the diagram, find the torque exerted by the force about the center of the knot. So the torque will be force times distance. 15 is in cm, so you convert that cm to meters. That will be divided by 100. So that will be 0.15 times 2.5. So that is the answer to number 1. Number 2 says, find the type of rotation caused by the torque. If you look at the arrow is going up, isn't it? So it's going from right to left, which is anti-clockwise rotation. So the rotation is anti-clockwise. If it is coming down, that will be clockwise. So here is another example. It says, find the force needed to balance the lever. So here we are given, remember that clockwise moment is equal to anti-clockwise moment. So this is anti-clockwise moment. Here, we have anti-clockwise moment. We have clockwise moment. So this will be 20 times 12 is equal to 8 times F. So F will be 20 times 12 is 240. Over 8. So that would be 30. 30 Newton. So F will be 30 Newton. F will be 30 Newton. So here we have another example. We are asked to find F2. We are asked to find F2. So remember, anti-clockwise moment, which we have here, is equal to clockwise moment. So here we have 2 times 5 plus 1 times 2. 2 times 5, anti-clockwise moment, 2 times 5 plus 1 times 2 is equal to 3 times F, F2. So 2 times 5 is 10. 1 times 2 is 2. That would be 12 divided by 3 is equal to 4. So F2 is equal to 4 Newton. So that is our answer. I hope you are all following.
Yes, sir.
So here is another example. You walk through it, and then you have exercises to play around with. So go through the exercise. I've sent a slide to your class governor. Go through the exercises and some of the examples, go through them, practice them. Anywhere you have challenges, let me know. So I have